Hello, everyone. We're just about to begin our presentation today on the subject of measurement of and handling of hydrogen and moisture in transformers. I hope that everyone can hear me well today. A few things before we begin. I guess, again, very warm welcome to everyone, and we're glad to have you here with us today for this event. Excuse me. There are going to be probably questions during the presentation, so as not to interrupt the presentation, you can ask those questions in the text chat, and there will be somebody in the text chat to answer your questions. Also, we have this streaming on YouTube, and for the people out on YouTube, you can also ask your questions in the chat, and if you want to join our presentation in Zoom, you can ask somebody in the chat, and we'll give you a link to join. One more thing, some of you may want to receive a certificate of being here today, and if so, also ask in the chat, and somebody will get back to you later on and get that certificate to you. Some of the questions we may not be able to answer during the presentation. This has happened in the past, but all of your questions are recorded, and it doesn't matter. We will still get back to you even if we don't answer your question specifically during the presentation. We will definitely get back to you, and you will have your answer after the presentation. Okay, so with this out of the way, I guess we can begin and go back to the presentation itself. So I hope we are ready to start the presentation, right? So the topic for discussion today is going to be moisture and hydrogen in transformers. Both of these components in transformers are indicators of certain degradation processes. Moisture can be the result of the destruction of oil or paper, or it may come from the environment, which can also be a problem. Hydrogen, on the other hand, is one of the gases that are constantly formed and generated when electrical or thermal faults occur inside the transformer. And the correct measurement of these parameters and management of these parameters is rather critical if we wish to extend the service life of our transformer units. Next slide, please. So when we talk about moisture, I guess the first thing we have to determine is where it comes from. In transformers, there are quite a few ways in which moisture enters the unit. There are different ways in which the transformer can generate moisture on its own. Some of the ways can be limited or reduced by what we do, and some of the processes occur regardless of what we do. So this is a dynamic process of the moisture formation in the transformer. Some of the main reasons for the increase of humidity inside your transformer are as follows. We can have residual moisture from the manufacturing processes. Transformer factories do strive and do their best to reduce moisture, but this is not done in all factories, and there are some factories where residual moisture is higher. And there are some factories that do not prepare oil before filling it, or there are even factories that do not have winding drying systems that make the equipment, and they produce the equipment with high levels of moisture to start with. Another form of moisture ingresses into the transformer after poorly done repairs. So there are processes during repairs in which moisture can come into the transformer and have a certain influence on transformer windings. A transformer repair company must implement systems that prevent moisture from the environment from being absorbed in the transformer. In addition, such shops must be equipped with oil treatment systems, because any negligence in these processes can increase the humidity in the transformer, and that will create certain problems in the future. Another way for moisture to enter the transformer is that the transformer actually absorbs moisture from the environment, because we have water vapor in the atmosphere, and this usually happens when the transformer is not airtight, when there are leaks in the transformer. If we can observe the point where there are oil leaks, that will become the interface between the environment and the transformer, and this is where moisture will come from. Because transformer, the pressure inside the transformer changes, the transformer is breathing. When the load increases, the temperature increases, and pushes the makes the metals in the transformer expand. And at this point, we will see oil coming out of the transformer at leak points. But when that unit cools down, the metals that it's made of also cool down, and this causes the compression inside the transformer with negative pressure. Now, gases from the environment, from the atmosphere, enter the transformer and bring moisture and maybe other contaminants with them. There is also the process that makes water form inside the unit, because aging oil and insulating paper will all contribute to the formation of moisture inside the transformer in this way. Let's go to the next slide, please. All right, so during oxidation of oil, water forms as a byproduct of that reaction. And in this case, there is a certain advantage, is that oil has high solubility of water, so it doesn't result in free water, but oils with high moisture content can foam when we degas the oil. It's always recommended to process the oil to achieve a low moisture content before filling the transformer with that oil, because paper in the insulation system has a very high affinity for water. It absorbs water very easily. And the greatest amount of moisture, the biggest percentage of moisture in the transformer, is present in that paper. And this water causes decomposition of the paper fibers and causes irreversible damage that can lead to an electrical discharge in the transformer. When the oil is heated, the total water content does not decrease. It only increases the solubility of water in the oil. And in this case, the reduction of viscosity achieved by heating the oil provides faster separation when there's free water, but the general amount, total amount of water in the transformer remains the same, and the dissolved water content actually increases. Next slide, please. So, okay, the formation of hydrogen in transformers occurs as a result of the destruction of the oil molecule. It's important to remember that oil is a hydrocarbon, so it's made up of carbon and hydrogen atoms, as the name implies. There is a long chain. So when energy rises, and we can see this in the next slide, when energy increases due to electric current or high temperature, these things, the molecules separate, and the atoms separate from this molecular chain. So we have free atoms in the insulating liquid. And these atoms have a certain energy, which will allow them to rearrange themselves into different compounds. Hydrogen, for example, the atoms of hydrogen can clump together, forming actual gaseous hydrogen. But this process can also generate quite a few other gases, such as methane, ethane, ethylene, acetylene, and others. And this rearrangement is one that we use extensively for gas chromatography. And there have been statistical studies that allow us to to find out the actual malfunctions associated with other gases. There are two processes of gas emission in the transformer. If the gas produced contains hydrogen and hydrocarbons, this indicates the breaking of the carbon-hydrogen bonds in the oil by electrical discharge. And this process is known as gasification. However, if the released gas does not contain decomposition products, the process is known as dissolved gas emission. So both forms of gas emission are fundamental and very important to keep track of in high voltage electrical equipment. Next slide, please. All right, so in terms of hydrogen, the production and buildup of hydrogen in transformers is normal, or I guess usual, with any thermal or electrical problems in the transformer. We can pretty much guarantee that hydrogen will be the only gas that will be generated for all of the faults that occur in the transformer. So it's very common to find large quantities of this combustible gas in our transformers in case of thermal or electrical faults. If the gas is produced in large quantities, the resulting bubbles pose a hazard to the transformers. They can cause electric discharges due to the poor insulating properties of the gas as compared to oil. Hydrogen is associated with low intensity problems, but as we can see in this graph in this slide, it actually is generated by all faults. So when studying faults of greater intensity, the characteristics of gases are used for gases for the formation of which more energy is required, but still we will always register continuous buildup of hydrogen. So this is why there is a series of sensors that only monitor hydrogen level. And this allows us to know if there is a change in the operation of the transformers. And it's also usually one of the highest concentrations in chromatographic studies. So knowing the amount of hydrogen in oil, it's a very good indicator for determining the efficiency of our thermovacuum processes and our degassing processes. Let's go next slide, please. So now we'll talk a little about the limiting values, some of the how much water and how much hydrogen can we have in the transformer for relative safety. Next slide, please. So water in the transformer is one of the elements that must be kept track of, monitored. However, it's one of the most difficult characteristics to control. There are several processes by which a transformer will generate moisture, and there are various parameters that all relate to moisture and will affect our attempts to keep the transformer dry. For example, our actions will always focus on reducing the amount of moisture in parts of equipment, which refers to the amount of moisture found free in the transformer. But there are other ways to determine moisture. For example, moisture present in paper and moisture dissolved in transformer oil. If we want to have a dry transformer, we must be sure that moisture is not contained in any of these forms. There are three forms, basically. So, for example, excuse me. One of the most difficult to handle is the emulsified water form. So the various states of moisture inside the transformer are interrelated with each other. They're not static because water can change and shift and move from one of these states to another. Since water in the paper increases or decreases with the temperature of the transformer, and it can go back into the oil or back into the paper. And so the solubility of water changes with the temperature. So we need to keep this low to reduce this interaction. So for this reason, it's recommended to always try to maintain a very low moisture level in the transformer, as low as possible. And this will allow us to extend the service life of the transformer unit. And we must remember that water is also a catalyst. It promotes rather harmful chemical reactions. These reactions flow faster and easier, and that has a direct impact on the service life of the unit. We know that oxidation processes, for instance, occur much faster in the presence of water, and that paper is also seriously affected when water is present inside the transformer. And these are just two possible problems that can arise in the transformer when humidity is increased. So it's very, very important to know the moisture present inside the transformer. It's necessary to understand that it's present there in different forms, and steps must be taken to correct that. It's important that during these adjustment processes, we do a good measurement of the moisture content so we can optimize our dehydration processes and know that these processes are effective or maybe ineffective, in which case they need to be adjusted. Next slide, please. So the amount of moisture in parts per million ppm in transformer oil varies with the depending on the type of the fluid. For example, this IEEE C57-106 2015 standard that we know and love specifies these values for mineral oil. So the amount of moisture in a transformer, first, it depends on when we take the measurement. We see that for the new oil, we have relatively low permissible or allowable values. Whereas for transformers below 69 kilovolts, we need a value of 20 ppm only. And for transformers above that, we need 10 ppm. So for transformers that are in continuous use, the values differ from the previous table. We'll see that there are 35 ppm values for a 69 kilovolt transformer versus 25 for 69 to 230 kilovolt transformers, and 20 ppm for transformers over 230 kilovolt. So in this case, the suggested values are presented for reconditioned or reclaimed mineral oil in transformers. And we see that for such insulating liquid, the voltage levels at which they operate is important. So for the transformer operating at less than or equal to 69 kilovolts, the value is 35 ppm. In transformers from 69 to 230 kilovolts, we got 20 ppm, and in larger transformers to 30 kilovolts and up, we'll have an acceptable value of just 15 ppm. Although it's desirable that the reconditioning process reduces that water content to, 10 parts per million or even less. For example, in silicone oil, however, these changes, these values change dramatically. So we have permissible ppm around 50 parts per million. While in transformers with natural oils, which are known for their high resistance to water, the values can be from 300 ppm to 100 ppm, depending on the voltages at which the transformer operates. So it will be 300 ppm for transformers less than 69 kilovolts, and a maximum of 100 ppm for transformers over 230 kilovolts. Moisture in ppm is only one parameter, though, so we also have to control the saturation of oil with water and the amount of moisture that is transferred from oil to paper, which are other very important constraints that we also must take into consideration. And we can go to our next slide. So standards define the acceptable moisture saturation values for mineral oils. So you can see these values depend also on the operating voltage of the equipment. If the transformer is less than 69 kilovolts, it's considered acceptable if the saturation value is less than 15%. It's questionable if this value is between 15 and 20%, and anything above 20% is considered unacceptable. So now if we look at the bottom of the table, the lower line, we'll notice that for transformers above 230 kilovolts, the saturation values are much more stringent. For transformers with voltages over 230 kilovolts, the allowable value is less than 5% of saturation. So from 5 to 7% is problematic, and anything over 7% is unacceptable. So saturation tends to seriously affect the breakdown voltage, especially when we test it in accordance with the ASTM D1816 standard, for instance. Next slide, please. Another important element to consider when determining moisture in a transformer is the amount of moisture transferred from oil to paper. There are various parameters that are used to determine this amount of moisture, most of which determine that a value greater than 2% is indicative of a wet transformer. We can see that IEEE 62 defines three values, which are subdivided as follows. Transformers with the percentage of less than 2 are considered dry transformers. Transformers that exceed 4% are considered excessively wet. Transformers that are 2 to 4% are extremely wet transformers, and it's recommended to carry out dehydration processes on them to extend their service life. There are also other standards that add other values to the scale. For example, the SIGRAY standard, which defines the value for new transformers. So for that, in that case, all those that are equal to or below 1 saturation are good or new transformers. IEC 6422 defines moderately wet, and extremely wet values, where 3.5 to 2% transformers are considered moderately wet or humid. Values above this range are considered wet or extremely wet. And high moisture levels in transformers are obviously undesirable, since paper is constantly being destroyed by this moisture, and there is a danger that the transformer may just stop working in a very critical way, critical failure. And such failures may even cause, the transformers to go out of service entirely. It may require some major repairs, and in some cases the transformer cannot be repaired and will have to be written off entirely. Next slide, please. So the permissible amount of gases now in the transformer, if we're on the subject of standards, will depend on different parameters. The first thing that needs to be taken into account is the relationship between oxygen and nitrogen, as we can see in this table. We have two large groups. On the one hand, we have transformers in which this ratio is less than or equal to 0.2. And the other large group includes transformers in which this value is greater than 0.2. So this makes it necessary to know other parameters in order to define our acceptable limits. We can also observe how age of the unit is important in determining the allowable values for the content of hydrogen and other gases. So we have four clearly differentiated groups where we have a value for those transformers whose age is unknown, a different value for transformers from 1 to 9 years old, and then another value for transformers from 10 to 30 years old. And finally, we have a specific value for transformers that are older than 30 years. Obviously, the values have a lot of variation there. So for transformers, the ratio of oxygen to nitrogen is greater than 0.2. If that is the case, then the maximum allowable values are 40 ppm. And with a ratio less than or equal to 0.2, there are three different acceptable values for transformers whose age is unknown. We can have an acceptable maximum limit of 80 ppm for transformers from 1 to 30 years old, and the maximum value will be 75 ppm. And for transformers over 30 years old, we will allow 100 ppm. So this mechanic must be repeated for all gases the transformers are tested for, and the permissible amount of gases must be less than any of the values indicated in this table here in this slide. Let's go next one. Right, so the unacceptable amount of hydrogen is determined in the same way as the allowable amount of hydrogen. We're going to take into account the same parameters which we will start the analysis with. So we'll start with the oxygen-nitrogen ratio and determine which section of the table we belong to, what we'll work with. And we determine the number of years of use of the transformer. Then we're going to determine the limits of the hydrogen content. So any value exceeding these limits will be considered unacceptable. We can see that the hydrogen values that are considered acceptable vary greatly. In transformers in which the ratio of oxygen to nitrogen exceeds 0.2, we should not have or must not have values higher than 90 ppm in any case. But for transformers with ratios of oxygen to nitrogen less than or equal to 0.2, this range is much wider, about 200 ppm, regardless of the transformer age. Now, if we think back and recall the previous table, we'll see that there is a range of values that are considered to be warning ranges, because if the hydrogen value exceeds the values from the previous table, but does not exceed the values in this table, we can determine that the transformer is in a problematic, questionable state, and it's necessary to conduct a deeper investigation of the characteristics of the possible fault problem, where we'll also take into account any values from other tests that we can perform, which is of great value for determining the exact possible fault and identifying the subsequent repair process. It's important to clarify that when we have a problem associated with the formation of gases, so we first tackle the element that generates the indicated gases, and only then we go and proceed with the degassing process. Because if the corrective measures are not taken regarding the gas generating fault, then the oil will have these gases generated again after we do the degassing, and this will all be for nothing. Next slide, please. So whenever we study transformer, the most important parameter is the rate of change. So whenever we have an abrupt change in a parameter, it's important to be able to determine what's causing this change. And it doesn't even matter if this change is still within the acceptable range. Any sudden inappropriate change means that there is an incipient problem in the transformer. The C57-104-2019 standard defines the values for the allowable rate of change between successive laboratory analysis. And this rate of change does not take into account the age of the transformer, but it does take into account the relationship between oxygen and nitrogen, and again, gives us two large groups, sections in this table where the values are less than or equal to 0.2. in this case, a rate of change of no more than 40 ppm is allowed. But when the ratio is more than 0.2, we can only have a maximum of 25 ppm rate of change. It's important to note that these changes are not directly related to the previous tables, because if the changes presented in this table take place regardless of the status based in oil levels, the transformer will be determined as a status 3 transformer. Next slide, please. So, okay, now we can talk about some of the more common problems that are caused by moisture and hydrogen in transformers, indicated by such. Next, please. The moisture saturation affects many oil parameters, such as power factors, interfacial tension, and breakdown voltage, but especially it's especially important for the breakdown voltage. We can notice some big changes, and this curve was developed by Vaisala. They used online measuring equipment that allowed them to know specific changes that occur in the oil characteristics, and they were able to measure and determine this curve of the breakdown voltage as a function of relative humidity of the oil. And we can see that at low moisture levels and saturation, we get very good values in terms of the RV in the oil. So when the saturation begins to increase, we can notice a significant increase in that characteristics. So a condition that's especially critical for high voltage transformers, since one of the components of the insulation system loses its dielectric characteristics. And we can see that if the saturation increases at levels above 40%, we will lose up to 70% of the insulating capacity. And as mentioned earlier, saturation greater than 5% is not recommended for transformers with voltages above 230 kilovolts. So knowing the moisture saturation of our oil is very critical for both the recovery process and for continuous operation of the transformer. Next, please. So moisture saturation is the ratio that links the amount of dissolved moisture to the total amount of moisture that can be dissolved. This value is usually expressed as a percentage. This means that 50% saturated oil uses up half of its water absorption capacity. Of course, these values are very small, and we're talking about quantities in parts per million, and this characteristic is seriously affected by temperature. For this reason, it's very important to know the temperature of the sample at the time of taking that sample, or to have equipment that can provide these values. An example of moisture saturation looks like this. So an oil with a temperature of 40 degrees centigrade has the ability to hold up to 120 ppm of water. And if the oil contains 24 ppm and the temperature of this oil is 40 degrees, so its relative saturation will be about 20%. And in this case, if the oil had a concentration of 60 ppm, that would mean that the saturation is 50%. So that's how it works. Next slide, please. So as we mentioned earlier, as you can see, temperature is a parameter that seriously affects the saturation of oil with moisture. And in this graph here, you can see the effects that the temperature has on 4 different types of oil. We can observe how mineral oil works at temperatures below 30 C. Its water absorption capacity is less than 100 ppm, but when the oil is close to 100 degrees, this capacity rises to about 900 ppm. The effect on silicone oils, lubricating oils, and vegetable oils changes very much, which changes the proportion of moisture that these fluids absorb. So another element to consider is that as the temperature drops, this dissolved water will separate from the oil. And this can cause us big problems if the amount of water released from the oil is large enough and sufficient to cause problems with the transformer. Or this amount of water may migrate into paper, or it can be, free inside the transformer, and this but paper will usually absorb that water, because one of the characteristics of paper is its very high affinity for water, and it really increases the percentage of moisture in the solid insulation. So the only way to keep moisture saturation low is to keep the humidity of the entire system low, because if we have high saturation, it will damage each and every element of the transformer, and we want to avoid that as much as possible. Next slide, please. All right, so Martin Engelhuber defines water as a slow but deadly poison for transformer, and this is 100% true. So what happens? Water reduces the breakdown voltage. That allows electric arcs to exist inside the transformer at lower voltage. Water accelerates the decomposition of paper, which directly reduces the life of the transformer. We must remember that the life of the transformer is always measured against the characteristics of the paper and the ability of the paper to withstand electrical and mechanical physical stress. Water causes oil aging. As we said, water is a catalyst. Catalyst accelerates these harmful chemical reactions that can occur inside the transformer. First of all is the oxidation of oil, and then destruction of paper, etc. Water reduces the mechanical or physical strength of paper. We all know what moisture does to paper. Its mechanical strength goes seriously down if paper is wet. We've seen how this happens, and it's the same inside the transformer. Wet paper is not very durable or not very strong. Also, water reduces the electrical resistance of not only oil, but of the entire system, which causes deterioration in all performance characteristics of the insulation system in total. We can see this in this graph provided by Sintef, which examines the effect of temperature in combination with water in solid insulation and determines the expected life of kraft paper. So on the blue line, we can see the expected life of the paper when it's completely dry. It's clear that as the temperature rises, the useful life is shortened. And now we can see in the purple dotted line, just below that, the effect of 1% moisture on the paper, which when operated at 80 degrees centigrade will give us an approximate life of 30 years, which is an okay value, 30 years. It's an acceptable value for operation of the transformer. But if we increase moisture to 3% and operate at 80 degrees Celsius, we can see that the service life is just 6 years now. And this means that we just lost 24 years of useful life of the transformer with the increase of the moisture content of the paper by just 2%. So this graph is a very good illustration of the importance of keeping the moisture in the oil and in the paper low. Next slide, please. So what we've said can be easily summarized into these two very small tables. Increasing moisture in paper will decrease the expected life of paper by about 60%. And for thermo-enhanced paper, this reduction of life expectancy is smaller, but still important because it's nearly 35% less than the expected normal life of the transformer. And with these numbers, we can easily understand the need for proper processing of oil and careful moisture control in the transformers and in insulating fluids inside the transformers. Next slide, please. So now to hydrogen. So the presence of hydrogen is usually associated with partial discharges, corona effects, and hydrolysis. Hydrolysis is a process in which water also forms, as we've seen. The processes of water formation that we've mentioned, which are very similar. The corona effect is an electrical discharge that occurs due to ionization of the gas that surrounds conductors, where the potential gradient has a certain value. This effect is usually observed on power lines with voltages nearing 30 kilovolts per centimeter. Partial discharges are incomplete electrical arcs or discharges, and they're all large hydrogen generators. These are typical transformer problems that need to be addressed whenever they're discovered to extend the life of the transformer. Let's go next slide. Now we'll discuss methods for measuring moisture and hydrogen in the oil. And straight to the next one, please. So the first thing to do is to quantify the problem. That is, we need to measure the amount of water in the oil and the transformer in general. And there are several ways to do this. We can have capacitive sensors. We can have laboratory methods, such as Carl Fisher method. We can take field measurements, such as dew point, and there are electrical techniques, such as frequency domain spectroscopy. And each of these methods may be convenient for us, depending on the actual situation. There will be some methods that are more reliable or more useful than others in a specific situation, but it's important to have reliable equipment in any case to be able to perform these measurements and meet our needs. Next slide, please. So the Carl Fisher method is a titration method for quantifying the amount of water in liquids. It's one of the most commonly used assessment methods today. So the sample is dissolved or suspended in a suitable solvent-free water, which is usually dry methanol, and an iodine reagent is added using an automatic dosage device. The water in the sample reacts with that reagent until it's completely consumed and free iodine is detected in the solution. The end point of the titration is determined voltammetrically with a platinum electrode. Karl-Fischer titration is used in various fields, such as determining the water content in food, or chemicals and drugs, cosmetics, and also mineral oils. This water content affects the physical and chemical properties of the products related to their freshness and shelf stability. In the oil industry, water is one of the most important contaminants, while in cosmetics, for example, it's one of the main components. And they need to control the exact amount of water to preserve their product properties. But Karl-Fischer, in general nutshell, Karl-Fischer is a very common method. Next slide, please. All right, the next thing we got is the capacitive humidity sensors. An electrical property of the sensor membrane changes depending on the moisture present. The membrane exchanges moisture with the dielectric oil, and it changes the electrical capacitance of the membrane. And then it's recorded and converted into moisture reading. And these sensors are pretty typical for field processes, and they're also available in GlobeCore products as an option. So these things are quite commonly used. Next slide, please. The dew point measurement. Now, the dew point of a gas is, the definition of this is that temperature at which the moisture begins to condense and precipitate on the surface that contacts with the gas. Based on this value, the total amount of water it contains and its relative humidity can be determined from a known volume. So the amount of water in paper is determined as a function of the relative humidity of the gas with which it contacts when it's exposed until equilibrium conditions are reached between the respective moisture levels. At present, enough experience has been accumulated to assert that this method for determining moisture content is correct and does offer sufficient accuracy. In general, the procedure is to fill the transformer with dry gas, can be air or nitrogen, in such a way that after a certain time, during which the state of equilibrium and humidity is reached, the dew point of the gas is measured, and this value helps us determine the residual moisture in the transformer insulation. Next slide, please. So dew point is converted into steam pressure or vapor pressure using graphs. So the temperature of the windings is measured, preferably by measuring the ohmic resistance, or the gas temperature is measured because after 24 hours in the transformer, the temperature is the same as the windings temperature. So from the measured value of the dew point and the pressure of the gas, it can be air or nitrogen inside the transformer, we determine the vapor pressure. And from this vapor pressure and the temperature of the windings or gas, the residual moisture is calculated, or rather determined using this graph, which is also known as the Piper plot. Next slide. Okay, so there is also the DFR frequency domain spectroscopy, and the results of the analysis show that the real dielectric constant and the imaginary dielectric constant increase with the decreasing degree of polymerization at the low frequency stage, while they remain unchanged at the high frequency part. Increasing the moisture content of the oil impregnated paper would increase the actual dielectric constant to 102 Hertz and the apparent dielectric constant throughout the frequency test. So the curve of the imaginary part, together with the increase in water content, will show a trend towards the right. Next slide, please. So the decision to perform oil purification and drying requires data on the correct state of the oil in the transformer. Besides, it's important to keep track of how efficient those processes are when we do them. The methods that we spoke earlier are to an extent indirect, and this is why GlobeCore is currently making the TOR product line available. This product line is designed to support oil recovery and regeneration in the field, But this equipment can be perfectly used as part of a laboratory indoors. TOR1 that you can see here is a device that is capable of measuring the amount of moisture present in the oil and its temperature. The important part is not really the parts per million measurement, the absolute content, but the indication of the activity of water in the oil. The device is compact, very easy to handle and carry around. It's very lightweight. Next slide, please. Basically, this device measures active water water activity with the capacitive sensor that gives us very good long-term stability, and it's very stable. It doesn't get interference from contaminants. The device measures physical quantities, water activity, and the temperature, these two. And with these values, the tester itself calculates the absolute content of water in ppm in the mineral oil. And it's also possible to set it up for non-mineral oils or lubricating oils like FR3 or what have you. You know, it's very adjustable and the process is very, very simple. Next slide, please. So as I mentioned, one of the main advantages of the TOR unit is simplicity. It really has the parameters that allow us to quickly read the moisture humidity in moisture content in the field. This device was specifically designed to be lightweight and very easy to handle. And water activity can be measured from 0 to 1, this range. Remember that this is a parameter that will determine how much moisture the oil has absorbed. And it allows the system to give us a reading from, calculate as a reading from 0 to 500 ppm with a much greater accuracy. One other thing that TOR1 measures is temperature. And this is done very quickly. That's good for field work. Besides, the unit only weighs like under 6 kilograms, and that makes it very easy to carry around and handle. But as I said, it's perfectly possible to use it as a part of any laboratory setup, and it will perform equally well indoors. Next slide, please. In addition to oil filtration and regeneration equipment, we got the TOR2 equipment machine, or rather instrument, which is designed to measure hydrogen content in the oil, and it also takes a measurement of moisture and temperature. So a standard laboratory test will take at least 1 day. If you take a sample, send it to a lab, it takes time. This can be a waste of time and human resources. It increases the cost of services. So this particular product allows the client, or the operator rather, to perform this test independently. We developed this device to provide accurate readings that will characterize the degassing and dehydration processes, reducing the time of work in the field and allowing the operator to safely diagnose the ongoing processes. So some of the important features of the TOR2 are as follows. Measurement of water content, ppm, again, from 0 to 500 ppm. It measures the temperature of oil from 0 to 55 degrees Celsius. And it measures the hydrogen dissolved in the oil from 25 to 5,000 ppm, if that be the case. The response time of this device is quite quick. It's under 60 minutes for hydrogen. It has very low cross sensitivity. Less than 2% interferes from other gases. And the power consumption is just 60 watt. And the dimensions are quite suitable for operation in the field. And the whole thing weighs under 10 kilograms, so it's also portable, can be used outside. Next slide, please. The heart of TOR2 is a sensor, and that sensor is coated with a special nickel palladium film. The film reacts to the presence of hydrogen. It changes its resistance in the presence of hydrogen, and that change is converted into an electrical signal, recorded, and stored by the same sensor. The change in electrical resistance is linearly related to the amount of hydrogen present in the sample of oil that we're testing. Next, please. So it's a very compact and robust and rugged sensor that allows us to effectively and reliably monitor the hydrogen content of oil. It's resistant to both environmental elements and to any interference and problems related to actually reading the parameter. For example, it does not require calibration. It's a self-calibrating sensor. It performs self-calibration at certain points in time automatically, so there's no need to worry about that for the customer, for the operator. Next slide, please. Now that we know how much of hydrogen and water we got in the oil, let's see what we can do about that. Next slide, please. Thermal vacuum is by far the most common method for dehydration of transformers, because it's a very highly efficient process and there is no consumables involved, such as absorbents and such. The thermal vacuum process uses the physical characteristics of water, or rather the difference of physical characteristics of water and oil, to extract that water from the oil. So it's well known that water evaporates at 100 C, 100 centigrade, but this is just half of the story, because if we are to describe this property completely, we should say that water evaporates at 100 degrees centigrade at 1 atmosphere of pressure. Now, the influence of pressure is very important in the boiling process, because when pressure is higher, so is the boiling point. And that indicates that these two are directly proportionate. When the pressure decreases, so does the boiling temperature. And this is important because we want to extract moisture, boil moisture, out of the oil without the need to heat it to the temperatures that can damage the oil. So what we do, we subject the oil to reduced pressure, or vacuum, directly affecting the water inside that oil, because now water can be extracted quite easily without damaging the oil by high temperature. The lower the pressure that we can achieve, the higher the vacuum, the lower the temperature that we need to apply to separate water from oil. And as we can see, this is a purely physical process. There is no chemistry involved. It does not depend on any consumables, such as absorbents, and it's completely tied to the physical properties of water, and this is it. So it's important to assure that the oil remains under vacuum for as long as we can arrange that, and that the surface area of that oil is the largest that we can achieve. That will extend the drying process, and it will also allow us to degas the oil, which is another added bonus of the process. Next slide, please. Once again, the use of thermal vacuum process allows us to remove gases from the oil, and apparently no other oil purification process can really accomplish that. So this is just it. It should be noted that thermal vacuum systems are effective for the extraction of water. So the thermal vacuum process is widely recommended as it affects a large number of possible contaminants in the oil, specifically gases and water. So the addition of hydrogen sensors to thermal vacuum oil purification rigs is a step forward in the quest for more self-contained, self-sufficient equipment that allows field diagnostics to determine if the oil has already reached the values that we aim for. And this eliminates the need to take samples and take it to an external laboratory to determine if the results that we wanted from the process have been achieved or not. Next slide, please. It's also important to know that the process it differs depending on how it occurs. So when we work on transformer paper, it's different depending on what part of the transformer we'll look at. So when we work on transformer paper, keep in mind that the extraction rate of water, it's not a linear, it's not a straight line. It will resemble the graph that you can see in this slide. The first stage is the heating process, and we can see here the increased amount of water extracted from the paper, and the rate increases linearly. In this graph, we can see this part that extends from point A to point B. Point A to point B. Points B to C, the little plateau here, it is the stability stage where the rate of moisture extraction is generally constant. In this stage, we remove moisture from the outer layers of paper. And next, we have a stage at which the rate of moisture extraction is greatly reduced. And this is due to the capillaries in the paper inside the transformer. Once we remove the water from the outer layers of the paper, the water in the inner layers of the paper starts going out and going through those thin capillaries. It must pass through that middle layers to the outside. And this is what causes this dip in the rate of water extraction. In many cases, this process will take a long time. Therefore, the moisture characteristics of the transformer must be carefully investigated in order to find the correct process, the appropriate process that will allow us to generally achieve the best results in the most efficient manner, to remove any water from the transformer and ensure that it stays dry and healthy for a long time and extend its lifetime as much as possible. So I suppose with this, I'd like to conclude this presentation today. This is all the information that we prepared for now. I'm sure we will come back to these topics again in the future, so stay tuned. We always have new things to discuss, and we have a lot of webinars planned for the nearest future. And I would like to thank you all very much for coming here and listening to us talk. And a big thank you to the people supporting this presentation who changed the slides and also answer your questions in the text window. Once again, I'd like to remind you, you can request a certificate of attendance for this webinar and from us, and you can also ask your questions still, and they will be answered. If some of the questions have not been answered so far, they will be, and somebody will contact you by email or whatever contact details you provided when registering. Once again, thank you, and I hope to see you all in the future in our next webinars. Goodbye.